All right, so we talked about parametric equations in 10.1. We're going to talk about polar coordinates in 10.2 and 10.3. And then in 10.4, 10.5, we'll talk about conic sections. And then in 10.6, everything will kind of get all tied together in a strange kind of way. Not that there aren't already some things that we could tie together now, but anyway, let's get into 10.2, polar coordinates. This should be review, okay? If it's not review, well, then that's why we're going over it, I suppose. But you know, you're going to want to make sure that you've got this material down pretty well, and let me know, you know, if this is like brand new, you've never seen it before, and you're really kind of freaking out about it all because it's just flying over your head or something, let me know, and I'll see if I can, you know, direct you to some material that you can use to kind of brush up. But anyway, but I'm going to kind of rush through this a little bit under the assumption that most of you are probably familiar with polar coordinates already. So here's the idea. In the rectangular coordinate system, points are described in terms of their horizontal and vertical distances from the origin. So for example, the point -3, 2 describes the point 3 units left of and 2 units above the origin. Right, there's the point -3, 2. All right. In the polar coordinate system, points are described in terms of the angle that they make with the positive x-axis and their directed distance from the origin. In this case, we call the positive x-axis the polar axis, and we call the origin the pole. So let's just practice plotting some points. So we'll plot the point 1, 3 pi over 2. The first coordinate gives you the radius. The second coordinate gives you the angle. So, and remember, the angles are measured counterclockwise from the positive x-axis, so from the pole, or from the polar axis, rather. Okay, so 3 pi over 2, pi over 2, 3 pi over 2 puts you right here. Radius 1 puts you right there. Okay. What about 0 pi over 4? Well, pi over 4 puts you at this angle right here, but a radius of 0 puts you right at the pole. What about 2 -4 pi over 3? -4 pi over 3. Well, let's see. There's -pi over 3, -2 pi over 3, -3 pi over 3, and -4 pi over 3. And the radius of 2 would put us right there. Okay. Let's show that the following polar coordinates describe the same point, right? So this is something that does not happen with rectangular coordinates. With rectangular coordinates, each point is unique. There's only one way to describe it. With polar coordinates, there are infinitely many ways to describe each point. So for example, 2, 11 pi over 6. So 11 pi over 6, we've got pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6 puts us right here. The radius of 2 puts us there. 2 -pi over 6. Well, if we measure positive angles counterclockwise, the negative angles go clockwise. And so -pi over 6 puts us right here, and a radius of 2 is the same exact point as part A. What about part C? 5 pi over 6 puts us here. But then r is negative, right? So the radius, instead of being a positive 2 out along this angle, it's a -2 out along that angle. And so sure enough, we end up at the same point. Okay? So multiple different ways that you could describe these things. Okay. One of the things that we want to be able to do when we're dealing with this new coordinate system is convert between what we knew before, the rectangular system, and what we're learning about now, the polar system, right? So to go from polar to rectangular, that is, if you know r and theta and you're trying to find x and y, then you use this relationship. X is r cosine theta, y is r sine theta. You can draw a picture to convince yourself of this. It's just a right triangle trig thing, right? So this is just a trigonometry thing if you've never seen it before. to go from rectangular to polar, that is when x and y are known, but you want to find r and theta, use r squared equals x squared plus y squared, and tangent theta equals y over x. Okay? Again, these are just right triangle trig things. That should be pretty clear if you draw a picture. Keep in mind that the hypotenuse of your right triangle is what r is, right? X and y are the legs, okay? And so then you should be able to see these relationships pretty easily. Okay, so for example, let's convert this point, which is given in rectangular coordinates, into polar coordinates. And since there are infinitely many ways to describe it, let's give the polar coordinate that has a positive radius and that has an angle theta between 0. I don't know why I switched from degrees to radians, but it should all be in radians. This is calculus. You should be dealing with radians. So from 0 to 2 pi. Okay, so we're given x and y. We want to find r and theta. So we're going to use these relationships. I'll find r first. Okay, so r squared is x squared plus y squared. That's 4 plus 4 times 3, so 12, which is 16. Oh, r squared is 16. How nice, right? So r squared is 16. That must mean that r is plus or minus 4. We want the positive one, so we'll take r equals 4, right? Okay. And then what about theta? Well, for theta, we're going to use this relationship, right? Tangent theta is y over x. So tangent theta is negative root 3. If you know the corresponding angle, right? If you know the angle such that tangent of that angle is negative root 3, if you just know that off the top of your head, that's fine. Otherwise, you can use your calculator and say, well, theta has to be tangent inverse of negative root 3, or some kind of pi multiple of that, right? So if you take tangent inverse of negative root 3 on your calculator, you get negative pi over 3. But negative pi over 3 is not between 0 and 2 pi. So what you do is you add pi, right? You add pi to it, and it'll give you another angle such that tangent of that angle is negative root 3. So if I add pi, negative pi over 3 plus pi is 2 pi over 3. And 2 pi over 3 is between 0 and 2 pi. You can check your work, right? What is tangent of 2 pi over 3? Plug it into your calculator if you don't know off the top of your head. 2 pi over tangent of 2 pi over 3, sure enough, is negative root 3. So this is the angle we're looking for. Okay. Of course, you could say 2 pi plus another pi would also be another one. What would that be? 5 pi over 3. So 2 pi over 3 puts you here. 5 pi over 3. So there's 3 pi, 4 pi, 5 pi over 3 puts you there. So no, it's going to give you a different negative 2 root 3. We definitely want to be in the one up here. We don't want to be in the one down here. I don't know. So drawing a picture is kind of a nice thing. Because technically 5 pi over 3 would also... No. Yeah, tangent of 5 pi over 3 is also negative root 3. So I guess the only way to know is to draw a picture. So let me explain maybe in more detail, right? What I did is plotted negative 2 and then 2 root 3, which is, I don't know, somewhere like around 3-ish, right? So it's that point right there, which means I should be in quadrant 2, right? I should be in quadrant 2. So the reason I'm not going to use theta equals 5 pi over 3, even though tangent of 5 pi over 3 is also negative root 3, is because that would put me over here in quadrant 4, and I want to be in quadrant 2. You could say, you know, theta equals 5 pi over 3 would work if you use r equals negative 4. because then that would put you back where you're supposed to be. Anyway, but we wanted a positive r, and so if we're forcing r to be positive, and if we're forcing theta to be between 0 and 2 pi, well then theta equals 2 pi over 3 is the only choice. Okay, so the polar coordinate, man, that took longer than I intended to take. But anyway, so the polar point would be, so r theta equals 4 2 pi over 3. Okay, and that's that. We can go backwards, convert polar to rectangular. That's a little easier. There's no ambiguity, right? We just say x is going to be r cosine theta. Y is going to be r sine theta. Cosine pi over 3 I think is 1/2, so this is going to be -3/2. Sine of pi over 3 is root 3 over 2, so this should be -3 root 3 over 2. So the rectangular coordinates x, y are -3/2 and -3 root 3 over 2. So that's that. Of course, we can do this with entire equations, right? So we can take a rectangular equation and put it into polar form. All we have to do is replace our x's with an r cosine theta and replace our y's with an r sine theta. If you see an x squared plus y squared, remember that that's the same thing as r squared as well. Not that it wouldn't work to still make these replacements. You could. It just takes a few more steps. But what I noticed here is that this is r squared. And this is going to be 4 times x can be replaced with r cosine theta. And that's that, right? That's really all there is to it. That's in polar form now. We like to try to solve for r if possible. In this case, I guess you could. You're not going to get a single value, but what you could do is you could kind of think of it like this. This is r squared. I mean, let me just say, this is a perfectly fine answer. Okay, that would be perfectly fine. But if you wanted to try to solve for r, you could think of this like r squared plus 4 cosine theta times r, plus 0 if you like, equals 0. And then you can use the quadratic formula. Right? You can say r equals -b plus or minus the square root of b squared minus 4 times a times c. Is there an easier way to solve for r? Well, there is, right? You could just factor out an r and then say r equals 0. Oh, okay, better yet. I mean, we can finish it this way. 4 times a times c would just be 0 over 2a. So you get r equals -4 cosine theta plus or minus, absolute value of 4 cosine theta. I'm just going to say, since we're already doing a plus or minus thing, that, anyway. So if you have -4 cosine theta plus 4 cosine theta, that's 0. So you get r equals 0, or if you do -4 cosine theta minus 4, you get -8 cosine theta divided by 2, which would be -4 cosine theta. So you end up with, I guess, two separate solutions. But there's an easier way to do that, which I don't know why I didn't think about it, and that is that you could just factor out the r. And then say, all right, so r equals 0, or r plus 4 cosine theta equals 0, which would mean r equals -4 cosine theta. And anyway, it never hurts to see the same thing worked out in a couple different ways. But that's that. All right. Going the other way around tends to be a little bit more difficult because you have to be a little bit creative. All right. So for example, if I saw the equation r equals 5, this is a polar equation. And if I think about it, what it's saying is that the radius has to be 5, regardless of what the angle is. So that should just be a circle with radius 5, if you think about it. And how do you write down a circle with radius 5? We would call it x squared plus y squared equals 25. But how do you arrive at that algebraically? Well, what you could say is, well, I could square both sides of this equation. If r equals 5, then r squared equals 25. And r squared, remember r squared is just x squared plus y squared. And there you go. For part B, we've got theta equals negative pi over 3. So here we have kind of the opposite scenario of part A. What we're saying is that the angle has to be negative pi over 3. R can be anything. So if you think about that, what you should get is just a straight line. Now, so a straight line is going to have, y equals mx plus b or whatever. But this straight line is going to go through the origin. So really it should just be like y equals mx. We just need to figure out what the slope is. But how would you recover that algebraically? Well, what you could do is you could say, I know that I need to get x and y in here somehow. I also know that tangent theta equals y over x. So if I take tangent of both sides, then tangent theta can be replaced with y over x. Tangent of negative, oh, I always have to think these through. I could just use my calculator, but I know tangent of negative pi over 3 should just be negative tangent of positive pi over 3. And tangent of pi over 3, goodness, so sine of pi over 3 is root 3 over 2, so it's root 3 over 2 over 1/2, so it's root 3. So I think this is negative root 3. Oh, we just did that on the previous page. I don't know why I didn't think of that. But anyway, solving this for y equals negative root 3 times x. And there you go. So the slope of this line is negative root 3. So you'd go down about negative 1.7 and over 1. Okay. Part C. We've got r equals secant theta. Oh, well, okay, so I can call this, I know that secant is 1 over cosine theta. And if I multiply both sides by cosine theta, now I've got r cosine theta equals 1, and I know that r cosine theta is just x. So this is just a vertical line. It's a vertical line, which is kind of interesting. What about this one? R equals 2 sine theta. If I multiply both sides by sine theta, I would get r sine theta here equals 2 sine squared theta there. R sine theta can be replaced with y, but 2 sine squared theta, I'm stuck there. I could square both sides and do r squared, which I could then replace with x squared plus y squared, equals 4 sine squared theta. But then I'm still stuck with the 4 sine squared theta. I don't know how to replace that with x and y. Another thing I could do, instead of squaring both sides, is I could multiply through by r. If I do that, I get r squared equals 2r sine theta. And this is good because r squared is just x squared plus y squared. R sine theta is just y. And there you go. This is some kind of circle, right? To get it in standard form, you'd have to move the 2y over, complete the square, do all kinds of stuff. I think what you end up with is x squared plus y minus 1 squared equals 1. I think. Okay, I'd have to actually work out the algebra. But at this point, you've done what you set out to do. You've replaced all the r's and thetas with x's and y's. So that's that. All right. Okay. Now the next big thing, and this is what we really want to focus on, is graphing polar equations, right? And of course, if we can convert polar equations to rectangular equations, then why bother graphing polar equations? You could just you could just convert them to rectangular form and then graph the rectangular equations. Well, here's the thing. Not all polar equations are going to convert nicely to rectangular equations. If you try to make the change, you could end up with something really nasty, like horribly nasty. And then second of all, even if they did convert nicely, it wouldn't guarantee that we would know how to graph the rectangular equation we end up with. So we're better off just dealing with it, right? Just learning how to graph polar equations. Kind of a naive way to do it is to just plot points. So let's practice, right? So let's graph r equals 2 plus 2 sine theta by plotting some points. First of all, I know that the period of sine theta is 2 pi, so I fully expect to get different values all the way around the unit circle, right? So all the way from 0 to 2 pi. So I'm going to plug in several values. And if I need to, I can always come back. If I need to, I can always come back and plug in more stuff, right? But here's what I'm going to do. I'm going to plug in for sure 0. I'll do pi over 4. I'll do pi over 2. I'll do 3 pi over 4. I'll do pi. That gets me halfway around. I'll do, what did I say? So pi, so that's 4. So 5 pi over 4. 3 pi over 2. And 7 pi over 4. And then that gets me back to 2 pi, which should give me the same value as 0, since sine of 2 pi equals sine of 0. So let's see. Sine of 0 is 0, so this should be 2. Sine of pi over 4 is root 2 over 2, so this is 2 plus root 2, so it's like 3.4-ish. Sine of pi over 2 is 1, so this should be 2 plus 2, which is 4. Okay, and then there's some symmetry here, right? Because sine of 3 pi over 4 is the same thing as sine of pi over 4. So again, I should end up with like a 3.4 there. I should end up with a 2 here because sine of pi is 0. At 5 pi over 4, I think I get something new because sine of 5 pi over 4 is negative root 2 over 2. So times 2 would just be negative root 2. So this would be 2 minus root 2. That's like 2 minus 1.4. So it's about 0.6, I suppose. At 3 pi over 2, sine is negative 1. So we have 2 minus this is just 0. Okay. And then at 7 pi over 4, I should end up with the same answer as I ended up with 5 pi over 4, about 0.6. If that's all too quick for you, pause, right? Rewind, rewatch if you need to. Use your calculator. But yeah, this is what we're getting. So when theta equals 0, r equals 2. When theta equals pi over 4, r is about 3.4. 1, 2, 3.4. We'll say right about there. When theta equals pi over 2, r is 4. 1, 2, 3, 4. When theta is 3 pi over 4, we're back out to 1, 2, 3 and a half-ish. A little less than a half. At theta equals pi, r equals 2. At theta equals 5 pi over 4, r is 0.6, a little more than a half. At 3 pi over 2, r is 0. And at 7 pi over 4, r is back out to about 0.6. And then at 2 pi, we kind of start all over again. Now, the cool thing about polar coordinates is that if you'll connect the dots in order, I don't know, I think it gives you a better idea of what you're dealing with. So, and keep in mind that these are usually curves, so you're probably not going to have like a bunch of sharp edges, right? I mean, these things are all continuous and everything. With the exception maybe of that point right there, which seems like it's got to be a sharp edge. So that's the picture you come up with, roughly speaking. Now, if you wanted to be absolutely certain that that's what that looks like, then you could go back and fill in, like you could plug in pi over 6, you could plug in pi over 3, and all of the same things in the other quadrants, or for that matter, I mean, plug in pi over 12, or 5 pi over 12. 5 pi over 12? Pi over 2, 3, 4, 5, yeah, 5, of course, and then 6 pi. So yeah, 5, so you could plug in 5 pi over 12, whatever. I mean, you're allowed to use your calculator, so. But I'm fairly confident that that's what that thing looks like. Okay. That said, sometimes these things can be misleading. Like sometimes you're dealing with this stuff and you have you end up with like a little inner loop type of situation, which technically we haven't like ruled out that might be something that happens here, right? So it's good to maybe develop some intuition. And the best way to do that, I think, would be to just memorize what certain families of these kinds of graphs look like. The book goes into all kinds of details about like symmetry and testing for symmetry and things like that. We kind of talked about it briefly just by noticing that like, hey, these values are going to have to be the same because sine of pi over 4 is the same as sine of 3 pi over 4. And same thing here, right? And same thing here and stuff like that. So we kind of talked about symmetry. The book goes into a lot more detail about symmetry. You're welcome to read up on that stuff. Personally, I don't think it's totally like terribly important. But what you should do, as I said, is really familiarize yourself with certain families of graphs. And so I have a chart on the next page that you should just like try to commit this information to memory. So some common types of graphs. These things are called limacons. That's French for snail, because I guess this looks kind of like a snail to a French person. I mean, I can kind of see it. Okay. Anyway. But this one is one of the ones that I was just talking about on the previous page, where you actually have this little inner loop thing. But what's nice is that it tells you when it happens. It happens if a over b is less than 1. So by the way, in this format, we're dealing with a and b where we're assuming that they're both positive numbers. So if you have something like a plus b cosine theta or a minus b cosine theta, you just take a and divide it by b if that answer is less than 1. So in other words, if a is less than b, you end up with an inner loop. If they're equal to each other, you end up with a cardioid, which again is like cardioid, cardiac, heart, right? It's a heart, right? It's a heart shape. Okay. That's the one that we saw on the previous page. And that happens if a over b equals 1. In other words, if a equals b. So like in the previous case, a and b were both 2. So we end up with a cardioid. You can end up with some dimpled limacons depending on, again, like the ratio of a to b. You end up without a little dimple, but maybe a flatter side than the other if a over b is bigger than or equal to 2, right? So these are the limacons. Now, something to point out here is that all of these that are pictured here, they're all of the form a plus b cosine theta. A limacon of the form a minus b cosine theta would bulge out to the left instead of to the right. So this would be something like, oh goodness, this would be something like 2 minus cosine theta would look something like this. If you had 2 plus cosine theta, it would be the mirror image flipped this way. Okay, so it would bulge out to the left instead of bulging out to the right. It kind of point to the left. So this is for an a plus b cosine theta. A minus b would flip the other way around. If you had a plus b sine theta or a minus b sine theta, then it bulges up or down. Right? It bulges up. So again, this thing pictured here is like 2 plus cosine theta. Is that right? 1 plus 2 cosine theta, because we need 1 divided by 2 to be less than 1. Okay, so this would be like 1 plus 2 cosine theta. If you had 1 plus 2 sine theta, it would look exactly like this, but rotated 90 degrees. So it would be pointing upwards, right? And if it was 1 minus 2 sine theta, then it would be rotated 90 degrees clockwise, so it would be pointing kind of downwards, right? So that's the way that the Lima psalms work. You've got rose curves that they look like this. The thing to notice about, so rose curves have the form a cosine n theta or a sine n theta. N tells you how many petals you have. If n is odd, then you have n petals. So in this case, n is 3, so you have 3 petals. If n is even, then you have 2n petals, right? So in this case, n is even, it's 4, so you have 2 times 4 petals, so 8 petals, and sure enough, right, 8 petals. Same thing goes for sine. If it's odd, you have that number of petals. If it's even, you have twice that many petals. Notice also that the sort of length of the petal is this number out here, right? It's A. So the length of the petal is always A. Another thing to point out about how roses work is that if it's a cosine rose, then the first petal is on the polar axis, like this one and this one. Okay, so that first petal is right there on the polar axis. And then the rest of the petals are evenly spaced. So, if you know that you have 3 petals, then you can say, well, to get all the way around the unit circle, I have 2 pi radians. So, so if I divide that by 3, then that's 2 pi over 3. So if my first petal is at 0, then my next petal has to be at 2 pi over 3. And then the petal after that has to be at 2 pi over 3 plus 2 pi over 3, so that's 4 pi over 3. And then the next petal after that has to be at 2 pi over 3 plus 2 pi over 3 plus 2 pi over 3. That would get you to 6 pi over 3, in other words, 2 pi. So it gets you back to that first petal. Okay? If it's a sine rose, then the first petal is at pi over 2 divided by n. Now, why is that? Well, that's because the biggest that sine 5 theta can ever get is whenever sine of 5 theta is equal to 1. When does that happen? Well, that's going to happen whenever 5 theta is equal to pi over 2. And when does that happen? That happens when theta equals pi over 2 divided by 5, right? So in general, if you've got r equals a sine n theta, then the first petal is at pi over 2 divided by n. And then, once again, the petals are evenly spaced. So, like, if you know that there are 5 petals, like there are here, and that the first one happens at, well, it would be pi over 2 divided by, so pi over 10. So the first petal happens at pi over 10. Okay, so then the next petal is going to happen at 2 pi divided by 5 is, well, just 2 pi divided by 5. Pi over 10 plus 2 pi divided by 5, that would be pi over 10 plus 4 pi over 10, which would be 5 pi over 10, which is pi over 2, sure enough, right? And then the next one, you would add another 2 pi over 5, and then 2 pi over 5, and then 2 pi, so they're evenly spaced, okay? Anyway, so that's how rose curves work. We've got circles and lemniscates. R equals a cosine theta looks like that. R equals a sine theta looks like that. If they're negative, then the circle would open up this way or this way. A lemniscate is the same sort of thing, but you've squared both sides. So that's what a squared sine 2 theta, a squared cosine 2 theta. These actually don't come up quite as much, but I don't know, they could surprise me. You've got spirals as well. Just think about it. I mean, plot some points and you'll see that you get this spiral in both cases. In addition to these, you should also recall what we kind of saw on the previous page, and that is that r equals a is just the circle centered at the pole, right? So it's different than these kinds of circles which have a side tangent to the pole, but a circle centered at the pole, right? A circle that's just centered at the pole like this, well, that would just be r equals a, okay? Where, well, actually, I guess it would have to be like this because they've already put a on here. So it would really have to be this circle. This is r equals a, okay? And then similarly, theta equals k is just a straight line through the pole at angle k. So like theta equals pi over 4 would, theta equals pi over 4 would just be that, right? This is theta equals pi over 4. All right. Anyway, play around with these things a little bit in Desmos to get a better feel for them. It's actually a lot of fun. Let me show you. Let me show you how to set this up in Desmos. So you can just type in the polar coordinates just exactly the way that that they show up. So okay. So let's say that we wanted to look at the equation, like we wanted to look at a Lima sum. R equals 1 minus 2 cosine theta. Right, then it just gives it to you. Now, if you want to switch the axis system to polar, click on the little wrench, and then click on that, and there you go. Right? So beautiful. Change it to plus and watch what happens. See? It just switches around. Change this cosine to a sine, and it goes up, right? And change it to a minus, and it'll point downwards. You can play around with these numbers to see how they interact. See, cardioid, when you make them equal, right? Inner loop, that way. What if you go like that? See a little dimpled edge. Inner loop again, right? So you can kind of play around with these things. You can play with the roses too. Like R equals 2 sine 2 theta. Okay, boom, right? If you make this A bigger, then it just makes the rows bigger. If you change the number of petals, 3, 4, 5, 6, 7. So you start to get a feel for these things, right? Anyway, you can do the same thing with, like, if I change this to cosine, what's going to happen? This petal is going to end up down here. The whole thing's just going to rotate, right? Cosine. See? In fact, you could graph them. 6 sine 9 theta. It's actually a lot of fun to play around with these things. We can make little pretty designs. Aw, isn't that nice? Maybe I'll change it to a sine. So that, oh, look at that pretty flower. Okay. So play around with it in Desmos a bit so that you kind of get your bearings. How long have I been going here? 38 minutes. Okay, we have some time to do a couple examples. So let's run through these 4. So, okay, so graph the following polar equations by using the chart on the previous page to identify its type. This is a rose for sure. It's a rose. The petal is going to be 4 units long, and they're going to be 3 petals. Not only that, but it's a sine rose. Okay, it's a sine rose, which means the first petal is not going to open up right on the x-axis. It's going to open up at pi over 2 divided by 3. That's pi over 6. So it's going to open up here along pi over 6. So 1, 2, 3, 4. There's the first petal. And then these things are evenly spaced, right? They're evenly spaced. So I know that I'm going to have, well, shoot. I mean, if I take 2 pi and divide it by 3, I get 2 pi over 3. So pi over 6 plus 2 pi over 3. Oh, goodness gracious. Pi over 6 plus 2 pi over 3 is pi over 6 plus 4 pi over 6, which is 5 pi over 6. That puts me right here. 1, 2, 3, 4. And then if I add to 5 pi over 6, if I add another 4 pi over 6, then I get 1, 2, 3, 4, and I'm 1, 2, 3, 4 right there. And so, you know, that's what it's going to look like more or less. Now, the only thing I don't really know for sure is like how wide or skinny the petals are, right? Maybe they're really skinny or maybe they're really wide. So I think the best thing to do probably is to figure out, well, you know, what's going on, let's say at like pi over 4, for example, right? So I'm just going to plug that into my calculator. So I have kind of the parameters set, right? Like I know what to expect. I'm just trying to figure out like how wide the petals are. If I plug in pi over 4, so I have 4 times sine of 3 pi over 4. That's 2 root 2, which is about 2.8, 2.9. So here I would be at 1, 2.9. And what if I plug in pi over 3? I mean, I'm just gonna get 0, right? I'm just gonna get 0. Ooh, okay. So pi over 3 is kind of like the tangent line where this swoops in. So I kind of get the sense that that's how thick the petal is. And of course, this thing is symmetric, right? They're all beautifully symmetric. So that's about how thick I expect the petal to be. From there, I mean, it's really like you just do your best. This is what I'm thinking. So that is the way that it gets traced out, by the way. If you actually plot the points, it gets traced out in that trajectory, which is kind of cool. Anyway, so that's that. So that's graphing a rose. Another rose, right? This time it's a cosine rose, which is a little bit easier actually, because I know that these things, the first petal opens up right at 0. So that just makes things easier. And I know that these petals are also 4 units long. 1, 2, 3, 4. Maybe a challenging thing about these is that, well, so n is even, so I know that there's actually twice as many petals as it seems. So there's not going to be 4 petals, there's going to be 8 petals. 8 petals. Where are they going to be? Well, they've got to be evenly spaced. So it's got to be here, 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 and here. That's where the petals are. If I want to figure out, you know, about how thick these things are, I could plug in something like pi over 12, negative pi over 12, to kind of figure it out, right? If I plug in pi over 12, goodness, 4 times pi over 12 would just be pi over 3. Cosine of pi over 3 is 1/2. 1/2 times 4 is 2. So pi over 12 would be out at 2. So right about here. So it seems to me like these petals are not going to be very thick at all. They're going to be kind of skinny. And I kind of sense that if I plugged in pi over 6, I would end up at 0 probably. Let's see. 4 times pi over 6 is, so that's 4 pi over 6, which is 2 pi over 3. Oh, maybe not. Maybe not. Where do I end up at 0? I end up at 0 whenever cosine of 4 theta is 0. That's going to happen whenever 4 theta equals pi over 2, right? So that would happen at pi over 8, actually. So it's pi over 8. So a little bit before then, I'm going to end up back at 0. Anyway, moral of the story is this, right? It's got to look something like that, right? That's what the first, but wow. And see, it doesn't cross pi over 6 because, like I said, it's 0 at pi over 8. So these petals are really, really skinny. Oh, and I don't know what the trajectory is. I think what happens is you start here and you come around and then you go down maybe? I don't know. But it doesn't matter. I'm just trying to draw the picture. And I know that it's going to look something like this. Ooh, that was bad. Anyway, so something like that. You can probably do a lot better than that. Okay, this guy. Gotta be a limacon. And not only that, a over b is 1/2, which is less than 1. So this is a limacon. Wow. Has it been a long day for me or what? Limacon with, so it's a limacon with an inner loop. That's good because I know what to expect. This is a cosine one, so it's going to bulge out, and it's a minus, so it's going to bulge out to the left, right? Bulges left. So these are good pieces of information. So since I know that it bulges left, I can try to figure out, well, how big is it going to get, and what's the inner loop going to be, right? So the biggest the thing is ever going to be is when cosine theta is 1. And that happens, or no, that's not true, right? The biggest it's going to get, because we're subtracting, so the biggest it's going to get is when cosine theta is -1, because then -1 times -2 will be +2, and this will be 3. So when is cosine equal to -1? It's equal to -1 here at pi, right? So I know that at pi, r is going to be 3. What's the smallest that r can get? Well, when theta is +1, then I'll be subtracting 1 minus 2 and get -1. When does cosine equal +1? That happens when theta equals 0. So at 0, I'm over here at -1, and that must be my inner loop. Okay? So that's kind of how limacons work. That's not a lot of information to go on, but at least you know that it's going to come out to here, and that its inner loop is going to be out to here. What more can we say? I mean, I suppose like we could just plug in some of the standard things. Like we could plug in pi over 2. Cosine of pi over 2 is 0, and r would be 1. Same thing with 3 pi over 2. How far out does it come this way? I kind of... We're starting here. When theta equals 0, we start at this point. And so I'm not sure when you're going to get back to the other side. I mean, we could just, if we plug in pi over 4, we get root 2 over 2. You get 1 minus root 2. So at pi over 4, you're still at a negative value. It's going to be 1 minus 1.4. So like negative 0.4. So it's going to be like negative a half. So like right there. So that's still part of that inner loop thing. So yeah, it doesn't look like we can get out of there. If we do, I mean, I suppose, well, no. If we do 3 pi over 4, cosine is going to be negative. So this is going to be 1 plus 1 point, so it's going to be like 2.4. So 1, 2.4, so that's not going in the direction that I really need it to. By symmetry, you'd have the same thing going on down here. And, well, let's see, by the time you get to 7 pi over 4, at 7 pi over 4, you're going to get a negative, so you're going to get that same kind of symmetry. But there must be a point at which you get Gosh, it's got to cross over. Well, anyway, you end up with something like this. Does it ever equal? Oh yeah, it'll equal 0 whenever cosine theta is 1/2, right? Okay, when is cosine equal to 1/2? That happens at pi over 3. I should have just plugged in pi over 3, right? Because that's when I get to 0. So at pi over 3, I get to 0. So that must mean that like right here at 5 pi over 12 is when you just barely sneak over. Let's verify that. Cosine, so I'm going to do 1 minus 2 cosine of 5 pi over 12. That comes out to, yeah, it comes out to like half. So, you know, you'd be like right there at 5 pi over 12, and then r is 1/2. So yeah. Anyway, so this is the inner loop, and then you go this way. And then by symmetry, you'd come up kind of like that, and then finish out the inner loop. That's what that one looks like. Okay, what about this one? Another cardioid. We kind of did almost this exact one. We did r equals 2 plus 2 sine theta, or maybe it was 2 minus 2 sine theta. What did we do? No, we did 2 plus 2 sine theta. This one is 3 plus 3 sine theta. It's going to be the same thing. A cardioid. It's going to be so it's cardioid. Pointing up. Not pointing up like you would imagine a heart, but I mean like it's going to bulge. It's going to bulge up. And I suspect, you know, when sine theta is 1, this is going to be 6. Sine theta is 1 when theta is pi over 2. 1, 2, 3, 4, 5, 6. Okay, so that's like the tippy top of the heart. When is it 0? It's going to be 0 whenever sine theta is negative 1, because then that would be 3 minus 3. And that happens, well, that happens at 3 pi over 2. So at 3 pi over 2, you're going to be at 0. I suppose we could ask what happens when theta equals 0. When theta equals 0, sine theta is 0, and you just end up with 3. And kind of the same sort of thing is going to happen at, well, exactly the same thing is going to happen at pi. So you can kind of see, all right, so you've got this heart. I'm not sketching this out in the correct order, because technically you'd start here, work your way around, but it's going to have to come up and bulge like that. Let's figure out, I mean, like what's happening at, let's say, 5 pi over 4 here. So let's see, 3 plus 3 sine of 5 pi over 4 is about 0.9, so it's like right there. And by symmetry, you'll have the same thing kind of on the other side. All right, so that lets me know kind of how flat to expect this to be. But I know that it doesn't have an inner loop, right? I know that for a fact. I have a feeling this is a little fatter than what I drew. Just based on this business, like it seems like it's got to continue out kind of like that, more fat. Yeah, that looks a little nicer. Okay, that's that one. And again, you can check all of this in Desmos, right? But I'm pretty confident that what we've done is correct. So that's all I have to say about that.